for joining. Today we're joined by Dr. Darrel Kingfield from GSL. He is the Hazard Services Program Manager at GSL, and he's going to be presenting to us some considerations during severe weather operations on dual polarization information as well as VCPs. So Darrel, I will start the slideshow here, and you tell me when to step forward.
Great, thanks. So thanks for the introduction. So this is a project that I've been tinkering with for about 6 years, and its conclusions were published in the February 2022 issue of Weather and Forecasting with the American Meteorological Society. So you can always reach out to that publication if you want some more information. But in general, the study examines a decade of decisions on how we choose to scan the atmosphere and its effects on both National Weather Service warning decision making, its skill, and how we observe thunderstorm hazards from radar. Next slide. So the United States has one of the most comprehensive Doppler radar networks in the world that was built throughout the 1990s, and today consists of about 159 S-band Doppler radars covering the continental United States and selected locations abroad. One of the key benefits of using S-band radars is that these frequencies are not easily attenuated and can see long distances from the radar dish, which really makes them optimal for scanning weather phenomena. Next slide. And even with only a few radars in place, their benefits in identifying hazardous weather were immediately recognized. In an initial study by Polgar and co-authors in 1994, sites with the WSR-88D were 5 times more likely to issue a tornado warning for a storm that ultimately produced a tornado. And there was a 20% decrease in the number of unwarned tornado events. And this support was further solidified by the National Academies of Sciences report, as shown in the slide here, that the WSR-88D is a major component of the entire atmospheric observing system and is the primary means for detecting, describing, tracking, and nowcasting thunderstorms and their attendant hazards. Now today, new National Weather Service forecasters, such as yourselves, have to take over 40 hours of specialized training on radar data collection and interpretation as part of your onboarding process with the Warning Decision Training Division. So the point I'm really driving home here is that the WSR-88D network is still really at the forefront of our observation ability to detect and track thunderstorms and their attendant hazards. Next slide. So we'll dive deeper into how the radar collects data. On the next slide. There we go. So each radar scans in a 360-degree circle at various elevation angles relative to the radar horizon. A collection of these elevation angles together is what we call a volume of data, and the strategy that decides what angles are scanned are called a volume coverage pattern, or VCP. So in the example on the right, we are showing VCP 12. This volume contains 14 elevation angles that span from 0.5 degrees to 19.5 degrees above the radar horizon. Most of you probably already know this, but I just want to make sure that I have all the vernacular down so it makes sense when I go through slides in the future. Next slide. So different VCPs have unique strengths and weaknesses that forecasters can choose from depending on the kind of information they want to receive from an ongoing or impending precipitation event. For example, VCP 12 provides for more dense sampling at lower levels of the atmosphere, while 11, which doesn't exist anymore, was meant to provide more dense sampling at higher levels of the atmosphere. And VCP 21, which also doesn't exist anymore, but did exist in our data set, really provided fewer elevation angle scans, but all the scans had a much better data quality. Now, in addition to these VCPs, there are VCPs 212, 211, and 221, which scan at the same elevation angles as 12, 11, and 21, but perform their velocity, range folding, and corrections differently. This algorithm is called SZ2 and is recommended for use when dealing with tornadic damaging wind or events that require velocity interpretation further from the radar. So at its heyday, there were about 7 non-surveillance VCPs that were available, but this number has really declined in recent years with VCP 215 coming online. It did basically abolish a lot of these other volume coverage patterns. But for the sake of our study, we had a lot of VCPs to go through. Next slide. So in addition to VCPs really changing over time and new algorithms and data quality improvements being implemented, natural disasters with service assessments that cause catastrophic damage can really also spur improvements. For example, after the EF5 rated tornado struck Joplin, Missouri on May 22, 2011, it was revealed that the storm had a very rapid low-level intensification, and most of it occurred between the lowest elevation angle scans, which at the time was around one look at the lowest levels of the storm every 5 minutes or so. And it was recommended in this service assessment report that more VCP sub-strategies be implemented that really rescan the lowest levels of the atmosphere more frequently. Next slide. And this ultimately led to the creation of 3 new supplemental scanning strategies that could be attached to existing volume coverage patterns. Supplemental Adaptive Low-Level Scanning, or SALES, was rolled out in 2014, and it adds 1 extra low-level scan to the middle of the volume collection. Multiple Elevation Scan Option SALES, or MESO-SALES, was introduced in 2015, and that could add 2 or 3 additional low-level scans throughout the volume. And finally, mid-volume rescan of low-level elevations, or MERL, which can rescan the lowest 4 elevation angles, 0.5, 0.9, 1.3, and 1.8 degrees a second time. So in each of these animated figures on the slide, you can see the radar beam will drop back down to scan the lowest 0.5 degree angle or more before reaching the 19.5 degree angle above the radar horizon, which, to date still signals the end of the volume. Next slide. So ultimately, there are pros and cons to these strategies. The main pro is that the mean time between scanning the lowest elevation angle drops when SALES is activated. This produces upwards of 71% more low-level updates on a thunderstorm every hour. But unfortunately, scanning that lowest elevation angle is the most time-consuming angle in the volume and results in ultimately fewer mid to upper level scans in the atmosphere. So really anything beyond 0.5 degrees or 2.4 degrees if you're using MERL above that radar horizon could be delayed anywhere from 4.5 minutes to 6.5 minutes between successive scans. Next slide. Now, right before SALES was implemented, there was really a larger modernization effort made to the radar hardware, and that was to support dual polarization capabilities. And this allows for both a horizontal and a new vertical pulse to be transmitted and received by the radar. And the inclusion of this vertical information really allowed for the scrutinization of the vertical dimension of targets, giving us a better idea of the size, shape, and variety of hydrometeors and other targets measured within that radar beam. Now, this allows for new base products to be available, such as differential reflectivity, or ZDR, which by definition is the ratio of horizontally polarized reflectivity to vertically polarized reflectivity and is proportional to the aspect ratio of hydrometeors that are small relative to the radar wavelength. So in the interpretation example on the right, the addition of a ZDR field can really give us a lot more information about this convective cell. So if you can go ahead and click. So the region with moderate reflectivity at horizontal polarization collocated with low to moderate ZDR signals that there's likely small to medium drops in this part of the storm. Click again. Higher reflectivities and even higher ZDR values signal that larger drops are likely falling in this region of the storm. And one final click. And finally, there's an even higher reflectivity region with ZDR near 0, and this should boost confidence that hail is falling within this region, because a ZDR near 0 signals that the targets in the beam are spherical in nature and really cannot be small given the magnitude of the reflectivity. So just the addition of ZDR in this instance really can break out the microphysical characteristics of this particular convective cell. Next slide. And as a result, dual polarization radar has been a game changer for scientists to scrutinize the microphysical characteristics of precipitating systems, with many new signatures observed and documented. For example, the ZDR column, which is defined as a region where raindrops are being lofted above the environmental freezing level, resulting in a positive ZDR being measured in a region where ZDRs typically would be muted. This signature alone has been documented as being a proxy for updraft location, can assist with hail nowcasting, be an identifying characteristic as to whether a thunderstorm is severe or not, and can also serve as a predictor of peak tornado intensity in a recent paper by French and Kingfield in 2021. And the example on the right shows that the ZDR column as an elevated region above that ZDR above the freezing level. So that just gives you an idea of what this can do. Next slide. So ultimately, researchers and Weather Service forecasters have received some very big advancements in how we collect information from the atmosphere and the types of information that are collected. Many sites received their dual polarization upgrade and then the ability to use sails with only about an 12 to 18 month gap. So it's possible that much of the data that has been collected in the polarimetric era could have fewer scans at mid to upper levels of any storm. And there are really a lot of unknowns as to how much of an impact that has. Next slide. And this ultimately really led to several questions that we wish to address in this study. So there are a lot of VCPs available out there, and we first wanted to know what the breakdown was of VCPs first being used between severe thunderstorm and tornado warning operations, and that were near tornado, hail, and thunderstorm wind reports. Second, we then wanted to see, well, how often was sails, mesosails, and MERL being activated during the warning decision-making process, and nearby storms producing tornadoes, damaging hail, and winds. Third, we wanted to know if warning performance improved when the closest radar was using a sail strategy. And in conjunction with warning performance, we wanted to examine if sail strategies were more likely to be used when widespread organized thunderstorms were forecast for a region. And for that, we brought in Storm Prediction Center watches. And finally, we really wanted to determine how long a single radar volume of data takes to scan over time, and how that value has evolved over the past decade, and really associate that back to the detection of a common polarimetric signature, which in this study we used as the ZDR column. That's why we defined it earlier. Next slide. So to start answering these questions, we first had to collect a lot of data. So the warning data set did come from the National Weather Service Performance Management website, where we parsed over 200,000 warnings to get the warning location, area, start time, and whether or not the warning was verified by a storm report. Now we used the warning tracking location to determine the closest what the closest WSR 88D was to that warning, and its issuance time to get the window of radar data to download. So yeah, for the last 10 years or so, whenever you used WarnGen and did drag me to storm, that point really mattered in this study. Next slide. And the thunderstorm hazard data set also came from the NWS Performance Management webpage, and we downloaded all tornado reports, hail reports with a size greater than or equal to 1 inch, or thunderstorm wind reports greater than or equal to 50 knots, as these were the hazard magnitudes necessary to verify a warning. We used the report location and the time to determine the closest radar and data window to download, and we understand that the storm data database isn't perfect, and there are possibly errors in report time, location, etc. However, given that we're analyzing over 250,000 storm reports, we really have to assume that a vast majority of these reports are correct, and any sort of errors would get washed out. Next slide. So with every warning and report having a closest radar and time window, the next step was to download an even larger amount of radar data. So we used the NextRad on Amazon Web Services to download a bulk of the level 2 radar files, and then we filled those gaps with the National Centers of Environmental Information, or NCEI data set to basically fill in those holes. And each warning or report had plus or minus 30 minutes of radar data downloaded, and we used the Python ARM radar toolkit to determine the VCP number and whether sails was running by looking at the order of the elevation angles in a volume. A volume with 1, 2, or 3 additional low-level scans was defined as sails X1, 2, or 3, and a volume with an extra scan of the lowest 2, 3, or 4 elevation angles was defined as MERL X2, 3, or 4. So overall, through this data collection process, we did find that 96% of warnings and reports had radar data meeting these time requirements and were ultimately included in this study. Now, I will note that we also analyzed a data subset, which corresponds to removing warnings and reports that occur within 30 minutes of the first one. And we did this to examine if there was any skew in the data introduced by outbreak events or events that occurred in heavily populated areas where you would get a high number of reports. And the sample sizes are shown in the table on the right. And the results from this subset actually effectively match what's in the full climatology. So in this presentation, we will be just reporting on the full climatology results, but you can defer to the paper for the data subset. The patterns are the same. Next slide. So we have a lot of questions we asked a lot of questions and we really need to start answering them. So first, let's talk about what VCPs are NWS forecasters using in their warning decision-making process, and were found nearby these thunderstorm reports. Next slide. So starting with NWS warnings, we see that forecasters opted for using VCP 12 or 212, which provides denser scanning coverage at lower levels of the atmosphere. So even with upwards of 7 VCPs to choose from over this data set period, over 86% of warnings in any given year were in VCP 12 or 212. And for tornado warnings, there was a greater ratio of warnings with the closest radar in VCP 212, as this is expected given the benefits of the SZ2 velocity de-aliasing algorithm. Now, other VCPs did account for a dwindling amount of warnings over time, with fewer than 5% in either warning type by 2014. Next slide. Thunderstorm reports follow a similar pattern to severe thunderstorm and tornado warnings, with at least 89% of reports having its closest radar in either VCP 12 or 212 in a given year. So since the beginning of the polarimetric era, VCP 12 or 212 accounts for at least 95% of all storm reports, and VCP 215, which again was introduced late in the data period, only makes up about 2% of those reports, which means that 3 total VCPs, each with the same set of elevation angles below 10 degrees above the radar horizon, were used in over 97% of storm reports. So ultimately, there's really a climatological consistency as to how the lowest levels of the atmosphere, below 10 degrees, are scanned over the past decade. Next slide. So the overall share of reports with a nearby radar running VCP 12 or 212 increased when looking at significant severe reports, which includes tornadoes rated EF2 or stronger, hail sizes greater than 2 inches, and wind reports greater than or equal to 65 knots. This is notable as it is these significant events that are more likely to be used for case studies and other scientific analyses of why certain thunderstorms produce particularly dangerous hazards. Next slide. So since there are 3 main VCPs that are being used nearby for most of the warnings issued and storm reports logged, these 3 VCPs are also where you'll find the greatest number of sales options for selection. And because of this, we focus the next part of analyses only on these 3 VCPs to determine how often these sales strategies are being used near warnings and reports. Next slide. So looking first at the usage of sales, mesosales, and MERL in the warning operations, we find that sales strategies were quickly adopted during their rollout starting in 2014, with over 71% of severe thunderstorm and 91% of tornado warnings using some sort of supplemental strategy in any given year since 2015. Sales 1 was the most likely used strategy with severe thunderstorm warnings, while Sales 3, with its 4 total lowest level scans, was most commonly used during tornado warning operations. So overall, since about 2011, about 40% of severe thunderstorm warnings and a quarter of tornado warnings were issued with no sales strategy running. However, most of these were prior to 2014, when sales was not even available. So as the years go on, we effectively expect a large majority of warning decisions to be made with some form of sales running, which again means that we're getting fewer looks at the mid and upper levels of the atmosphere. Next slide. Moving over to storm reports, we find that the hazard type follows a similar trend to the warning that is verified by that hazard type. Tornado events, which are used to verify tornado warnings, are more likely to be running a sales strategy with sales times 3, and this accounts for a majority of the reports since its first full year of implementation in 2016. Hail and wind reports, which more likely verify severe thunderstorm warnings, were more likely to have a sales strategy running, but it's likely to have fewer extra low-level scans, with sales 1 being the most common in nearly all years. So since the dawn of the polarimetric era, 3 out of every 4 tornadoes reported have had some sales strategy running, and around 60% of hail and wind reports have also had a sales strategy running. And so ultimately, since the beginning of the polarimetric era, a majority of thunderstorm hazards were scanned with more low-level scans and fewer upper-level scans. Next slide. When examining significant severe reports, slightly fewer tornado reports and more hail and wind reports had its closest radar scanning with some sort of supplemental scanning strategy. And we postulate this is because convective environments conducive to tornadogenesis are also producing these other significant severe hazards. So you were more likely to have a sales 3 strategy running in a tornado environment. You're likely going to be getting very large hail, very large wind reports at the same time. Next slide. So with this information, we know that in a majority of warning decision-making environments and storm reports, the closest radar was running some form of sales, mesosales, or MERL strategy. And this information brings us to our next question, which is whether this information being available at the closest radar to a warning decision-making point resulted in warnings that were more likely to be verified by a storm report. Next slide. So before we get into warning performance, let's get some information about our methods for this question. So for this analysis, we computed 2 performance metrics. The probability of detection, or POD, which is the percentage of hazards that were inside an appropriate warning, and the false alarm ratio, which is the percentage of warnings that did not have an appropriate hazard inside of it. So what is an appropriate hazard for a warning? Well, a hail report of 1 inch in diameter or larger, or a wind report of 50 knots or greater verifies a severe thunderstorm warning, and a tornado report verifies a tornado warning. However, we also have to consider the case of a hail or wind report falling inside a tornado warning. In the case, the report would be counted as being within a warning, hence boosting that hazard type's probability of detection, but the warning itself would not be verified, boosting that warning type's false alarm ratio. So in this study, we excluded these kinds of crossover reports from the analyses because we did not want to artificially inflate the POD for hail and wind reports, and rather focus on whether the forecaster issued the appropriate warning for the hazard expected. We also performed significance testing at this step by building a distribution of data using a non-parametric ordinary bootstrap technique and a one-sided Mann-Whitney U-test to evaluate whether more low-level scans corresponded to improved performance. Next slide. So here's a receiver operating characteristic plot showing both the severe thunderstorm warning performance as annotated in circles and the tornado warning performance as annotated in triangles. So severe thunderstorm warnings overall had a higher POD and lower FAR than tornado warnings, and both severe thunderstorm and tornado warnings that had its nearest radar scanning with 2 or 3 extra low-level scans, which is sales 2 or sales 3, or MERL, actually had a higher POD and a lower FAR than the national average, as annotated by the filled in black circle and triangle respectively. Furthermore, when comparing warnings issued with no sales running from 2015 to 2020 and comparing its performance to 2011 to 2014, both severe thunderstorm and tornado warnings saw a statistically significant decline in overall performance. And we attribute this to a lower overall use of a VCP without sales, particularly in recent years, compared to really having no options in 2011 to 2014. So, your no sales VCP was being used both for, outbreak and highly conditional or low probability severe weather events during this period. Next slide. So focusing in on the tornado warning portion of the plot shows the enhanced separation, particularly between sales 3 in terms of POD and FAR compared to other sales types. Sales 3 tornado warnings had a statistically significantly higher performance than its other scanning types, and a similar behavior was also observed between sales 2 and sales 1 or no sales. This trend was also observed when these warnings were segmented by year. Tornado warnings year over year tended to have a higher POD and lower FAR with sales 3 or sales 2 running compared to sales 1 or no sales. Next slide. Focusing in on the severe thunderstorm warning portion of the plot shows that sales 2, sales 3, and MERL all had a similar probability of detection, with around 84% of wind and hail hazards near a radar that was in this scanning mode occurring inside a warning. MERL, while only being used for a small fraction of all cases, did have the lowest false alarm ratio of all sales strategies, but we postulate this is because NWS training does recommend the usage of a MERL strategy when QLCS modes, which can produce severe hail in its developmental stage and more widespread severe winds during its mature stage. Both Sales 2 and Sales 3 were statistically significantly better than Sales 1 or using a no sales strategy, but not statistically significantly better than each other. So given this information, it may be beneficial to use Sales 2 for scenarios where severe thunderstorm warnings are going to be the more prevalent hazard in a convective environment to ultimately speed up volume scan collection times by about 30 seconds. Next slide. So given that we knew what events were verified by what warning, we also calculated what hazards had a positive lead time by supplemental scanning strategy. Here we define positive lead time as the hazard occurring at least 1 minute after the warning issuance time. So looking from no sales to sales times 3, we can see a large improvement in tornado reports with positive lead time, with only 35% of tornadoes with a radar running no sales, but 74% of tornadoes with sales 3 running having a positive lead time. There's also a positive trend seen with hail and wind hazards, but there's more of a plateau again seen between sales 2 and sales 3. There's only about a 1% increase in hazards with lead time at this stage, and it really further supports the claim that there's minimal added value between sales 2 and sales 3 in convective regimes where hail and wind are the anticipated hazards. Next slide. So we're seeing in general that warnings with a nearby radar running sales 2 or sales 3 tend to have a better performance or result in a better warning performance than its associated hazards, and have a better lead time than sales 1 or when no sales strategy is being used. But ultimately, is there another factor that could be triggering the planned usage of a sales strategy, such as the forecasted potential for widespread organized thunderstorms to occur? Next slide. So to address this question, we chose to look at severe thunderstorm and tornado watches issued by the Storm Prediction Center in Norman, Oklahoma. All watches from 2011 to 2020 are available on the SPC website, and we used the universal geographic codes and timing information from the product text to determine what warnings and hazards were inside of each watch type or outside of a watch area altogether. Overall, we examined about 3,700 severe thunderstorm watches and 1,700 tornado watches. Next slide. So folding this data set into our analyses does reveal several things. First, about 61% of severe thunderstorm warnings and 35% of tornado warnings occur outside of an SPC watch. Of the about 21,000 severe thunderstorm warnings issued since 2016 with no sales strategy running, 75% of these warnings were issued outside of an SPC watch box. And of the 721 tornado warnings issued since 2016, about half of these warnings also occurred outside of an SPC watch box. These percentages declined to about 43 and 32% of cases respectively when examining radars with 4 extra low-level scans. With an SPC watch out, offices inside that box were more likely to have a supplemental low-level strategy running. And for tornado watches, it was sales 3 for both severe thunderstorm and tornado warnings. But inside severe thunderstorm watches, it was sales 1 and sales 2, respectively. Next slide. So breaking down whether or not a severe thunderstorm warning was verified by an appropriate hazard by SPC watch type reveals that cases running with sales 2 had the highest verification percentage both inside and outside of an SPC watch box. Warnings with sales 2 or sales 3 nearby had a greater verification percentage than sales 1 or no sales outside of an SPC watch box, and a nearly equitable verification percentage inside of a tornado watch. So given these results on top of the trends that we've seen in performance and lead time analyses, there does not seem to really be a substantial benefit to using sales 3 or sales 2 when near storm environmental conditions are conducive to producing hail and wind hazards. Next slide. Performing the same analysis for tornado warnings reveals that a higher percentage of warnings with a nearby radar running sales 3 verified compared to warnings using sales 2, sales 1, or no sales. And when no SPC watch box was out, 33% of warnings issued with a nearby radar providing 4 low-level scans verified, compared to only 20% of warnings issued with the nearby radar providing only 1 low-level scan. So that's the no sales strategy. Next slide. So this leads us to our final question as to where we examine how mean radar update times have changed over the last decade with all of these new scanning strategies in place, and really how that would translate to examining any upper level atmospheric feature. Next slide. So in order to quantify how the adoption of sales strategies can cause a slowdown in detecting mid to upper level features, we decided to pick the ZDR column and determine at which elevation angle it would be seen at every storm report time and location. Now in this study and other studies, the location of a ZDR column has been defined as occurring around 1 kilometer above the 0 degrees Celsius isothermal level. And for every storm report in the study, we grabbed the closest 1 hour rapid update cycle or rapid refresh analysis grid, calculated the height above the 1 kilometer above the 0 degrees Celsius isothermal level, and then determined the radar elevation angle that would transect that height level. Next slide. And of the 189,206 potential ZDR column locations analyzed, 99.3% of these locations were found above the lowest elevation angle, and this includes all ZDR columns within 50 kilometers of a WSR-88D, which means that the selection of any sales strategy would increase the time between these higher scans by 31 to 93 seconds for VCP-12, 38 to 114 seconds for VCP-212, and 53 seconds for VCP-215. Next slide. Now, examining volume scan times for the most complete volume near a tornado report over the first decade of the dual polarization radar era, a notable increase in volume scan completion time can be seen as more sales options became available. From 2011 to 2013, around 16% of volumes near tornadoes were collected faster than what a standard volume of data would take to be collected. This was mainly due to the automated volume scan evaluation and termination, or AVSET software, that was installed at the WSR-88D that would terminate a volume early if minimal radar returns were discovered at 2 successive elevation angles at least 6 degrees above that radar horizon. By 2015, which was the first full year of Sales 1, 60% of radar volumes were taking at least 15% longer to be collected. And from 2016 to 2020, over 30% of radar volumes were taking at least 45% longer to complete. Now, these delays were not as bad for hail and wind reports given the usage of lower sales numbers, but overall, over 69% of hail and wind reports had its closest radar volume complete slower than normal, and 40% of these volumes were taking at least 30% longer to complete than, a decade ago. Next slide. So from 2014 to 2020, the median volume scan time near a tornado for VCP-212, which is the most commonly used VCP for that hazard, went from 297 to 368 seconds, so over a minute longer to complete a volume of data. For hail and wind reports, the median volume time takes around 39 seconds longer to collect. So over the span of an hour, these delays are resulting in at least 2 fewer scans per hour, but with more aggressive sales strategies being used today, this could mean 4 fewer scans per hour. And this ultimately has adverse effects on any radar feature you are trying to track at least 0.9 degrees above the radar horizon for sales or mesosales, and beyond 2.4 degrees when you're using MERL times 4. Next slide. So in summary, a lot of questions were asked in the study and a lot of topics were covered. So let's go ahead and present the highlights on what was found. So in the first decade of the dual polarimetric radar era, over 93% of thunderstorm warnings and 96% of tornado warnings and 95% of all storm reports were scanned with a volume coverage pattern providing more dense low-level coverage. This was using VCP-12 and 212. When sales, mesosales, and MERL came online starting in 2014, it was rapidly adopted and was activated nearby a majority of warnings and storm reports in recent years. Sales times 3, which provides 4 total low-level scans per volume, is most commonly used with tornado warnings today. And sales times 1, which provides 2 total low-level scans per volume, was most commonly used to support severe thunderstorm warning decisions. From a performance perspective, warnings issued with SAILS 2 or SAILS 3 had a higher POD and lower FAR, and a greater probability of hazards in these warnings having a positive lead time. And in several analyses, there was a negligible difference between SAILS 2 and SAILS 3 when it came to severe thunderstorm warnings and the nowcasting of wind and hail hazards. So it might, again, be advantageous to use SAILS 2 instead of SAILS 3 for more convective setups where hail and wind hazards are the predominant threat to really speed up the volume scan collection times. Now, while the data suggests that we should be continuing to use SAIL strategies during severe weather operations, especially for tornado warnings, there ultimately may be other factors that were not analyzed in the study that could also contribute to forecasters making confident and accurate warning decisions. In this study, we examined warnings inside SPC watches and found that SAIL strategies were more likely to be activated in these environments where there was the enhanced potential for severe weather hazards. However, we did find that outside of SPC watches, warnings supported by a nearby radar running SAILS 2 or SAILS 3 observation were more likely to be verified than warnings issued with no SAILS. And unfortunately, the rapid adoption of SAILS has resulted in increased volume scan times between successive scans, particularly at or above 0.9 degrees above the elevation angle at the radar horizon. And given that it is the NWS's mission to protect lives and property, I really don't see these scanning strategies going away, but we at least need to acknowledge that we are not seeing features at mid to low levels of the atmosphere as frequently as we were before. And this is especially the case for popular signatures like the ZDR column, which would be affected by this in over 99% of cases analyzed in this particular study. And just because the radar doesn't see it does not mean that it did not happen. So with that, I will go ahead and leave the slide up and take any questions.